Hello, let's talk about section 9.8, which is looking at mathematical models, three in general: linear, exponential, and quadratic. Especially with the present state of the world, I think we've all heard a lot and seen a lot of mathematical models. Very important in science, in projecting, as we can see what our government does with the stay-at-home orders, looking at mathematical models of what is the rate that people are getting sick, what is the rate of death of the coronavirus, and lots of other important factors. To make a mathematical model simply means to write an equation that's going to represent the data that you see. So there's a couple of ways. Our objectives is to recognize what type of function it is by the graph. So straight lines are linear functions, and they are the form y equals mx plus b. We've also looked at exponential functions. This was the growth rate of the virus, correct? It was spreading at an exponential rate, where b is the growth rate. B, the base here, is the growth rate. So y equals a times b to the x is our general form of an exponential function. And then now finally we've studied quadratics, and they have a shape of a parabola. So if you were to see data points in this shape, then we could model them with y equals ax squared plus bx plus c. Now there is a way that you can do this on your graphing calculator. Most of the time that method is taught in Algebra 2, so we are not going to do that. We're also not going to cover section 9.9 because that goes with that mathematical modeling. It's a little bit ahead of what we need to learn this year. So in the essence of time, trying to get everything we want to get done, we're not going to do the next section in chapter 9. Our next assignment will be the review, and then we'll do the test. Okay, so how could we choose a function looking at a graph? So if you had some points and you graph those, you would say this is an exponential, this is a linear, and this looks very quadratic. So you would want to, if you wanted to guess what is the next point on that curve, you'd first want to figure out, well, what type of equation, I need a quadratic equation to do that. So that's the first way that we're going to recognize what type of model is by the graph, and I've sketched them here. The second way that we want to determine which model best represents the data is from a table of values. So when you have a table of values on the very next page, it'll look like this. The x's are always on the top. Remember, that's the independent variable, and the y, or the dependent variables, those y values will be on the bottom. Now here's a pretty big assumption. We need to assume that the x values increase evenly. So if you were doing something in real life, you'd want to be aware of that. Since this is only Algebra 1, the models that we're giving, or the data points that we're giving, will increase by 1. Do you see how they're all very consistent? Okay. So if that's the case, then this is how we recognize that data is either linearly, exponentially, or quadratically related. It's another way to say it. So if it's linearly related, then the differences of the y values are constant. The differences of the y values, well, do you see this arrow? It's kind of deceiving. The difference of the y value, you go 1 to the right and subtract this guy. So 5 minus 2 is 3, 8 minus 5 is 3, 11 minus 8 is 3. So we have a constant difference of our y values. That would be a linear function. Now, how could we model that? Remember, for linear, we have y equals mx plus b. And our m is going to be that constant difference. The constant difference. So in this case, we had a constant difference of 3. That is our m value. Now, how do you find your b? How do you know this is b? Well, if you're given that x is equal to 0, whenever x equals 0, remember your b is called your y-intercept. So we can say our b is going to be 5. If we weren't given that, what if we were only given these data points? Then we could put 1 in for x and 8 in for y, and then solve it backwards. So 8 is equal to 3 times 1, we'd subtract that, and then we would get our b, our plus b would be 5. But I think for most of these data points, given linearly, they will give you your, when x equals 0, so that's your b. So that's how you found this equation from this data. Let's look at the next data set. If data are exponentially, best modeled exponentially, then the ratios of the y values is constant. The ratio of the y values is constant. So let's take a look at this chart here. The ratio, remember, is take one number and divide it by the previous number. So 0.5 divided by 0.25 would be 2. We're not subtracting, we're dividing a ratio. 1 divided by 0.5 is 2. 2 divided by 1 is 2. Do you see how we have a constant ratio? So that indicates to us that this would be exponential. And remember, the exponential is y is equal to a times b to the x. And here b is our constant ratio. B is the constant ratio. So whatever we found here, which is 2, we know that b is going to be 2. So we will do y is equal to a times 2 to the x. So how do we solve for a? Well, choose any random point in here, put them in for the x and the y, and that's how we will find our a. So again, the easiest point to use right here is 0. So if we took a look at this, let me write it down here. I'm doing number 2, doing some work down here. So we have y is equal to a times 2 to the x. We know it's 2 because that was our constant ratio here. Now we're going to put in 0 for x and 0.5 for y. So we have 0.5 is equal to a times 2 to the 0. And let me remind you that anything to the 0 is equal to 1. So 0.5 is equal to a times 1, or a is 0.5. So then our final equation would be y is equal to 0.5 times 2 to the x. And we have created a mathematical model that explains this data. And then we can extrapolate. We could say, well, when x equals 3, what would y equal? Well, we would just put it in here. 2 to the 3 is 8. Half of 8 is 4. So then we can, and this is how the president and other doctors and medical specialists now are trying to determine how many cases of the coronavirus they might see in the future. Once they get a model that they trust, then they can extrapolate and say, well, in 2 days it should be this, in 3 days it should be this, right? This is the same, very similar, simpler, but similar methods to what they're doing. And of course, if you listen to the TV at all, they're always adjusting the model, right? They're looking at new data. They're looking at new data and saying, well, what is the model now? Because in the real world, you very rarely get such nice, clean, where every point is on the line. All right, so now let's take a look at a quadratic model. Well, how you know that data can best be modeled in a quadratic equation is that the second differences are all constant. What do we mean by second differences? Well, we find the first differences here, just like we did with the linear. 2 minus 5 is negative 3. 1 minus 2 is negative 1. 2 minus 1 is 1, and 5 minus 2 is 3. Notice they are not the same, so this should not be modeled linearly. So we take the second differences, which just means to go down here and find the differences here. Negative 1 minus a negative 3, which is the same as plus 3, gives you 2. 1 minus a negative 1 is 2, and 3 minus 1 is 2. So our second differences are all the same. They are constant second differences. So quadratic models, the second differences are constant. Now here's an interesting fact. The fact that the second differences is 2 tells you nothing about the equation. All right, so how did they find this quadratic equation from this data? Well, that's really kind of an Algebra 2 problem. I could show you how to do it, but all of your homework problems are not going to be as complicated as that. When you find a data set that should be best mapped by a quadratic model, we're just going to use y is equal to ax squared. We're not going to use the bx plus c. It just is a little bit more complicated. So how do we do that? Well, let's find a problem where we can do that. In fact, let's do this guided practice right here, shall we? Okay. Tell whether the ordered pairs represent a linear function, an exponential function, or a quadratic function. And then here, it's not in a table, but we could either make a table or we could just look at these data points. Okay, so you know that the answer is going to be quadratic. But how would you do this? Well, let's take a look at the y's. Negative 0.5 minus a negative 1.5, that would be 1. 2.5 minus a negative 0.5 is the same as 2.5 plus, that's 3. So right away, I know that the first differences are not the same. So it's not linear. But let's go ahead and write down those first differences so we can see if, and you know what, I think I'm just going to make a table here. So here's our guided practice. Here's our x, here's our y. Going to write these points out in a table. So I have 0, 1, 2, 3 for my x. 0, 1, 2, 3. And for our y, we have, sorry, I'm down here, negative 1.5, negative 0.5, 2.5, and 7.5. All right, so negative 0.5 minus this, that's the same as plus, that's a positive 1. 2.5 minus that, that's a plus, double negative, that's 3. 7.5 minus 2.5 is 5. This is called our first differences. They are not the same, so it's not linear. So now let's find the second differences. 5 minus 3 is 2, and 3 minus 1 is 2. So our second differences are constant. So we know that this is a quadratic, or that a quadratic model best explains this. And then let's go ahead and try and find a good equation for it. So we have y is equal to ax squared. And then let's just go ahead and choose a point, right? So if x is 1, y is negative 0.5. And I'm using 1 because it's the easiest to do. 1 squared is just 1, and then we divide, so we know that our a is a negative 0.5. So now we can say y is equal to negative 0.5 x squared, and that would be the model for this data. If we wanted to extrapolate more points, we could go further in the future. That doesn't seem quite right to me. And you know, they may have given us data points that can only be modeled. I don't think this is quite right. I think with these data points, they've given us something that should be modeled by y is equal to ax squared plus bx plus c. So let me go ahead and find another example. Okay, so here's one that is a little bit simpler for us. Write an equation for a function. So first we have to find out which function best models it. 0.5 minus 2 is negative 1.5. 0 minus 0.5 is negative 0.5. 0.5 minus 0 is 0.5. 2 minus 0.5 is 1.5. They are not the same. Let's take the second differences. 1.5 minus 0.5 is 1. 0.5 minus a negative, which means plus 1. Negative minus a negative, which is the same as plus 1 is 1. So second differences. So this can be best modeled by a quadratic. Y equals ax squared. Choose any point. The easiest point is this point here. And we would have 1 squared. So a is equal to 0.5. So the equation is y equals 0.5 x squared. Why did I think that was not true here? Because when x is equal to 3, 3 squared is 9, and half of that, we don't get our points, right? So this is actually not a very good model. These data points, even though they are quadratic, they cannot be modeled by the simple formula. You'd have to model them like that, which we're just not going to do that at this point. So I hope that was not too confusing to you. This is the better example to take a look at. All right. Over here in example 4, last example, good for us to look at. You could subtract the data. You'll find that the first differences are not right. Find the second differences. They still are not constant. So if it's not linear or it's not exponential, the only model that we know outside of that is, it's not linear, it's not quadratic. So let's test for exponential. So the way we test for exponential is we take the ratio. So 57.1 divided by 51.4 is 1.11. 63.3 divided by 57.1 is 1.11. And just to speed it up, you can see that those ratios are all the same. So an exponential model, remember, is y is equal to a b to the x, and the b is the ratio. So we have y equals a times 1.11 to the x. And then what is our a? It's easiest to find a when x equals 0 because 1.11 to the 0 is just 1. So what is the, oh, and we don't have that, right? Okay, so this is a great example. So let's just choose any point. Might as well do this one. When the x, which stands the speed of the cyclist, is 20, then the breathing rate, which is the y, is 51.4. So we have to put that in here. A times 1.11 to the 20 is going to equal 51.4. Now, what do we do here? Well, we actually have to find out what is 1.11 to the 20. So 1.11 to the, use the caret, 20. It's not going to be real big. Oh, goodness sake. Sorry about this. Okay, 1.11 to the 20. And then I am going to divide 51.4 by this number, correct? Let me show you how to do that. 51.4 divided by, do your answer, second answer, and we get 6.37 or 6.4. I'm not sure how rough they're running that off. So A is about 6.38 or 6.4. We can see what they got here. 6.38 is what they wrote. Great. So now using this example, in example 4, suppose the cyclist is traveling at 15 miles per hour. Notice that we don't have 15 up here, but we can use the model to extrapolate backwards to what do we think the breathing rate would be. And this is the beauty of the mathematical model. Y is equal to 6.38 times 1.11. We want to know if he's going 15 miles per hour. Now we can just go ahead and figure that out. So we've got 6.38 times 1.11 to the 15. And you can do it just like that on your calculator. It will do the order of operations. And we expect that their breathing rate would be about 30.5. So Y should be about 30.5, and is that liters per minute. And that is exactly what the book has. 30.5 liters per minute. Okay, I hope you found this a little bit interesting. If you have any questions, just make sure that you post them in the stream or drop me an email. Take care.